At the beginning of the formation of young Earth, the cosmos was a chaotic but wondrous space where new planets were born in the depths of stellar systems. This process can be compared to a grand symphonic orchestra, where each note plays its role in creating harmony. Time in this context seems almost infinite. Billions of years, like drops of rain, fall into the abyss of the cosmos, creating an abundance of celestial bodies. Elements resulting from thermonuclear reactions in stars formed clouds of gas and dust, which gradually compressed under the force of gravity. These clouds, like majestic landscapes, formed protoplanetary disks where particles collided and united, creating primary planets. This process can be imagined as a builder starting with a small stone and gradually constructing a massive building, where each detail is important. Over millions of years, these early planets, such as Earth, were subjected to meteorite bombardment, which, like an endless rain, brought new elements and water, creating conditions for the formation of an atmosphere. As a result of these cataclysms, Earth, like a living being, began to acquire its individuality, and the processes occurring on its surface were so intense that they could have outshone the most dramatic events in human history. This epoch was rich in changes. Volcanoes erupted, forming new landscapes, and intense earthquakes created cracks in the crust, as if the planet itself was trying to break free. At this time, there was no life on Earth, but the conditions for its future appearance were already beginning to form. It is impossible to overestimate the scale of these processes, as they occurred within timeframes that human perception cannot encompass. We are talking about time measured in tens of millions of years, where each moment is an entire epoch. This cosmic theater, where stars die and are reborn, reminds us that each planet is not just a rock, but the result of a long and complex process that continues to this day. Looking back at this incredible process, we can ask how our planet looked in those distant times when nothing hinted at the appearance of life. Scientific research conducted by astronomers and geologists shows that Earth, like other planets, acquired its shape in a mode of an invisible dance, where each detail was important for the formation of what we know today. This dance continues, and each new step in the study of the cosmos reveals new mysteries that once seemed inaccessible. For example, the analysis of meteorites found on Earth allows scientists to look into the past and understand what the early solar system was made of. The formation of the protoplanetary disk around the young Sun occurred approximately 4.5 billion years ago as a result of the collapse of a giant cloud of cosmic dust and gas, known as the solar nebula. This cloud, primarily composed of hydrogen and helium, began to rotate under the influence of gravitational forces, leading to its compression and the formation of a spiral structure. During this process, the temperature inside the nebula reached several thousand degrees Celsius, causing it to glow, even in the dark depths of space. The brightness of this glowing disk contrasted sharply with the emptiness around it. The blackness of space seemed endless, while the disk, made of gas and dust, flickered like a mysterious luminous ribbon in the void. The particles in this cosmic dance moved slowly but inexorably, creating the conditions necessary for the further formation of planets. As gas and dust collided and adhered to each other, they formed larger objects that later became protoplanets. This process was not hurried but inevitable. Gravitational forces drew in more and more matter, creating majestic vortices and streams that gradually formed the structure of the solar system. Over millions of years, these protoplanets began to acquire their individuality. But at this stage, they were still raw lumps of matter that needed to be shaped into full-fledged planets. Within the disk, where the temperature was high, solid particles formed that later became the cores of terrestrial planets, while in the outer layers, where it was cooler, gas giants formed. This process, described in the works of such scientists as Imre Kertész and his colleagues, became the basis for understanding how our solar system came into being. It is important to note in this context that similar processes could have occurred in other stellar systems, which is confirmed by the observation of exoplanets and nebulae similar to the one from which our Sun emerged. Accretion is a process that begins with the smallest cosmic particles, just a few micrometers in size, which, while floating in the vast expanse of space, collide with one another and start to adhere. These collisions occur in conditions of almost absolute vacuum, where temperatures can fluctuate from -200 to +200 degrees Celsius. creating unique conditions for the formation of larger bodies. Dust particles of various materials, such as carbon, silicon, and metal, gradually approach each other, forming larger aggregates known as planetesimals, which can reach several kilometers in diameter. This process takes millions of years, and its speed can be compared to a slow dance of matter, where each collision is like a gentle kiss that gradually leads to the formation of larger and more massive objects. If we could observe this process, we would see dust particles moving in the airless space, colliding with almost hypnotic slowness, forming clumps that grow larger with each second. Similar to how snowballs on a mountain slope gradually increase in size, these cosmic bodies form from countless small particles, each contributing to the creation of something greater. Scientists like Dr. Martin Cox from the Institute of Astronomy in Cambridge study this process, using computer models to understand how these collisions occur and how they influence the formation of planets. Accretion is not just a physical process, but also a crucial stage in the formation of solar systems, where over billions of years, small particles form planets, moons, and entire systems. At each stage of accretion, the state of matter changes, from dust and small pebbles to large comets and asteroids that can reach sizes of tens of kilometers in diameter. Collisions do not always lead to fusion. Sometimes they can cause destruction, breaking already formed bodies into smaller particles, which is also an important aspect of this endless process. Each such stage of accretion is not just a physical interaction, but also a reflection of the complex balance of forces existing in space, where gravity, speed, and the angle of collision play a decisive role. Ultimately, accretion leads to the formation of planets where conditions for life can arise, making this process key to understanding not only astronomy, but also the very emergence of life on Earth. With the formation of planetesimals begins a crucial stage in the evolution of the protoplanetary disk, which exists in a young stellar cloud. Planetesimals are the first large bodies, ranging from several hundred meters to several kilometers in size, that start to form from gas and dust collected in the disk around a young star. Gravity begins to play a decisive role in this process. Small particles first collide and merge, forming larger bodies. These processes occur over millions of years, beginning roughly from 100,000 to several million years after the star's formation. As a result, in the vast cosmic space filled with countless small particles, planetesimals begin to emerge, gradually increasing in size. At this time, we can imagine a vast cosmos where thousands of rocky bodies orbit their orbits, collide with each other, explode, and form new structures. These collisions can produce such forces that they cause material ejections into the surrounding space, creating dust clouds and tails. The contrast between the solidity of these new bodies and the emptiness of space becomes particularly striking. Against the backdrop of boundless blackness and infinite emptiness, planetesimals resemble grains of solid matter that gradually gain mass and become increasingly massive. A key aspect of this process is that each planetesimal, reaching a certain size, begins to attract surrounding material, thereby strengthening its gravitational influence and allowing it to gain mass. Thus, the small rocky bodies that initially seemed insignificant eventually become the foundation for the formation of planets, thereby creating the basis for future planetary systems. It is important to note that planetesimals are not just random rocks. They are the first building blocks from which all planets, including Earth, are formed. Currently, scientists have estimated that the protoplanetary disk could have contained up to 100,000 such objects, each of which could have become part of the future world. From a protoplanetary disk filled with small particles and planetesimals, a long and complex process of forming proto-Earth began. Microscopic particles gradually aggregated, forming larger bodies due to the force of gravity, which acted on them like an invisible hand, attracting more and more material. This process can be compared to a slow awakening, where each new planetesimal added its share to the growing mass, like pieces of a puzzle coming together to form a single picture. When two planetesimals collided, they did not simply fly apart, but merged their masses, transforming into larger objects. This process of combination and fusion occurred so slowly that it seemed almost imperceptible. But over the course of millions of years, it led to the accumulation of significant volumes of matter. As a result of these collisions in space, bodies the size of small planets formed, which continued to grow, absorbing everything that crossed their path. Observing this process, one can imagine how a new planet gradually formed in the cold darkness of space, where each drop of matter, each new layer, was added to the existing ones, as if nature itself were creating its masterpiece. This process occurred with inexorable inevitability, as order emerged from chaos, and a multitude of small particles gave rise to something greater. Ultimately, when the mass reached a certain size, its gravity became strong enough to begin attracting other objects, further accelerating its growth. It is important to note that this slow and gradual process of forming proto-Earth contributed to the creation of stable conditions for the subsequent formation of an atmosphere and, eventually, life. The energy released during collisions also facilitated the processes of differentiation within the planet. As a result, heavy metals such as iron and nickel accumulated, forming the core, while lighter elements rose to the surface, forming the mantle and crust. Thus, this process of forming proto-Earth not only contributed to its growth, but also laid the foundation for geological processes that would determine its development for billions of years to come. The hypothesis of the giant collision with protoplanet Theia suggests that around 4.5 billion years ago, two large planetary bodies, one of which became known as Theia, slowly approached each other in the vast expanse of the early solar system. These two celestial bodies, each comparable in size to modern Mars, moved towards each other, their orbits gradually shrinking under the influence of gravitational forces. Over millions of years, they orbited in a cosmic dance that seemed peaceful, but laid the groundwork for a catastrophic collision. In the moment of impact, when Theia and young Earth collided, something extraordinary occurred. Not just destruction, but a true symphony of cosmic power. For an instant, the surfaces of both bodies collided with incredible force, approximately 500 million kilometers per hour, ejecting a vast amount of material into space, molten rocks and minerals that upon impact melted and formed a cloud of gas and dust, reaching hundreds of kilometers in height. This cloud of molten material began to rotate, forming a disk around Earth that would eventually cool and condense into lunar masses. Waves of molten material floating in space created a spectacle reminiscent of magnificent fireworks, where each particle of matter ejected into the open cosmos carried a fragment of the future. This process did not merely destroy, it created, from chaos, new bodies emerged that would eventually become the Moon, Earth's satellite, influencing its climate and oceanic tides. This moment of collision symbolizes not just the end of one era, but the beginning of a new one, where stability is born from cosmic chaos. The destructive cosmic dance, driven by the forces of nature, became the foundation for the further development of Earth and its moon. Scientific research conducted in recent decades has confirmed this hypothesis, and astronomers believe that such a collision could have led to the formation of the moon and the creation of conditions necessary for the emergence of life on Earth. After the collision mentioned by astronomers, the ejected debris began to move in an orbit around the young Earth. This process was not instantaneous, but took place over millions of years. Around Earth, a cloud of gases and particles formed, gradually beginning to thicken. Initially, these were small fragments, ranging in size from pebbles to large boulders. Over time, gravity began to attract these particles to each other, causing them to rotate and form an accretion disk. This disk consisted of debris that gradually coalesced into larger bodies. At this stage, the formation of the Moon was very slow, millions of years, as each new portion of material was added to the already formed core. Approximately 100 million years after the collision, when the main mass of debris had already gathered, the Moon began to take its shape. At this time, the space around Earth was filled with bright flashes and eclipses, as particles collided with each other, creating fireballs and ejecting flying chunks of material into space. During this period, the cosmic vacuum was filled with an amazing silence, and even in the chaos, there was a sense of grandeur. Each new debris piece, colliding with the Moon, left a trace in the form of craters, and these craters became evidence of how the Moon formed over countless eons. The young Moon may have had active volcanic activity, and its surface was covered with molten magma, creating lava oceans that gradually cooled and solidified into a solid crust. This process of forming the Moon from collision debris created conditions for its further development. Gradually, over billions of years, the size of the Moon stabilized, and its surface moved away from volcanic activity, allowing it to transition into a more peaceful state. As the Moon continued to orbit Earth, it found its place in the Earth's orbit, and this was not just movement, but a majestic dance of two celestial bodies that continues to this day. Ultimately, as the Moon acquired its final form, it influenced Earth, creating tides and stabilizing the planet's axis of rotation, which is crucial for the existence of life. In this context, the formation of the Moon became not just a physical process, but an event of immense significance for the entire solar system. As a result, by 3 billion years ago, the Moon had taken on the appearance we know today, with its craters, seas, and other features. After its formation, early Earth was a completely different world from what we know today. It was a giant sphere of molten rock, heated to such temperatures that its surface glowed, emitting a blinding light. Imagine standing on a planet with no solid crust, only a vast ocean of liquid magma, with waves crashing against invisible shores. Temperatures could reach thousands of degrees Celsius, and the air was filled with thick steam from the vaporized rocks. There were no mountains, forests, or any familiar landscape elements, only endless expanses of fire and lava flowing like rivers of molten metal. This hellish landscape, filled with hissing and crackling, was the result of intense volcanic activity as the planet continued to cool after its formation around 4.5 billion years ago. Collisions with other celestial bodies, including large objects like the planet Theia, created conditions for this catastrophic initial stage, when Earth was essentially a melting pot where all chemical elements were in a state of fusion. As a result, the atmosphere was filled with heavy gases like carbon dioxide and ammonia, making it completely inhospitable for life as we know it. This world was far from familiar, with its fluctuating temperatures and constant volcanic eruptions that sent clouds of ash and gas into the air, creating an effect of an endless sunset. In this state, the planet remained for millions of years until the process of gradual cooling began, leading to the formation of the first solid crust. During this time, Earth was slowly trying to take shape, but until the appearance of the first continents and oceans, this fiery sphere remained empty and lifeless, bearing no resemblance to the blue planet we know today. At this stage of formation, when life could not yet exist, significant changes in Earth's chemical composition occurred, which played a crucial role in creating the conditions necessary for life in the future. On early Earth, about 4 billion years ago, the planet's surface was submerged in chaos and activity, resembling a churning magma ocean. During this time, when the surface temperature reached over 1,000 degrees Celsius, magma formed giant waves that rose and fell like an ocean, but instead of water, it was a molten mass of rock. Imagine, streams of bright yellow and deep crimson magma surged, glowing and reflecting sunlight that pierced through clouds of dust and steam. These whirlwinds of molten rock created an indescribable scene, as if the planet itself breathed, spewing hot streams that crashed against cold crustal patches and returned to the depths. On the surface of the magma ocean, constant eruptions could be observed as hot material burst forth from the interior, creating craters and jets of molten lava like fiery fountains. The colors of this magma ocean ranged from bright orange to deep red, sometimes even approaching white when the temperature reached its peak. At such moments, the magma became so hot that it radiated light, like stars in the night sky. This activity created unique conditions for the formation of the first minerals and, ultimately, for the emergence of life, which, as we know, only appeared billions of years later. At this stage of Earth's history, the surface was not just a place, but a true theater of thermodynamic processes, where constant changes led to the formation of new forms of matter and the planet's structure. Each eruption, each lava flow played its role in shaping the environment that would one day become the home for future organisms. Thus, the magma ocean not only defined the landscape, but also set the fundamental conditions for the formation of the atmosphere, which later contributed to the emergence of life. The process of differentiation of the Earth's substance, which began around 4 billion years ago, represents a key stage in the formation of the planet's internal structure. In its early stages, Earth was a molten sphere with temperatures reaching several thousand degrees Celsius. In this magma ocean, heavier elements such as iron and nickel began to gradually sink towards the planet's center. This movement was not instantaneous, but occurred over millions of years, creating the unique internal structure of Earth. Initially, as the planet was still actively forming, heavier elements began to form the core, which eventually became the center of most of Earth's mass. The core, composed mainly of iron and nickel, occupies approximately 1/3 of the planet's total volume. Meanwhile, lighter elements such as silicon, oxygen, and aluminum sought to rise to the surface, forming the mantle and crust. This process of differentiation can be visualized as a slow but inexorable movement of matter, where each element, based on its density and chemical properties, found its place. For example, as a result of this process, the mantle, which lies between the core and the crust, is primarily composed of silicate minerals. The crust, in turn, became the thinnest and lightest layer of Earth, forming continents and oceanic floors. This layering occurred unevenly and under the influence of various factors such as temperature, pressure, and chemical composition. In the early stages of Earth's differentiation, when the planet was still young, this process was particularly intense, and all elements interacted, forming the first minerals and rocks. Interestingly, as the planet cooled further, the process of differentiation slowed down but did not stop, resulting in the complex structure we observe today. The first crust of Earth could have formed within a few 100 million years after its formation, but the final formation of all layers took much longer. The scientific community, particularly geologists and planetologists, continues to study this process to better understand how our planet was formed and how it has evolved over time. For instance, modern research indicates that some elements, such as hydrogen and helium, could have been captured by Earth during its formation, which also influenced the chemical composition of the mantle and crust. The process of forming Earth's iron core is one of the most significant stages in the planet's history. During the first few million years after Earth's formation, when the surface temperature was extremely high, heavy metals such as iron and nickel began to accumulate at the planet's center. These metals, with their high density, gradually settled to the bottom, forming a dense metallic core. According to scientists' estimates, about 70% of the core's mass is iron, while nickel contributes an additional 10%. This process, facilitated by factors like gravity and thermal influence, resulted in the formation of a massive pulsating ball of molten metal at the planet's center. Studies indicate that the temperature in this metallic heart reaches over 4,000 degrees Celsius, making it one of the hottest places on Earth. Geophysicists, such as Dr. Emilio Escobar from the Mexican University, emphasized that it was during this period that the core formed, which, as it cooled, became solid in its inner part, while the outer layer remained molten. This unique structure creates conditions for dynamic processes that, in turn, can influence the formation of Earth's magnetic field, although this topic requires separate discussion. Additionally, the study of seismic waves passing through the core has been conducted since the early 20th century, when seismologists began using earthquake data to investigate Earth's internal structure. These studies have shown that the core has a radius of around 1,300 kilometers and consists of two layers, an outer, molten layer and an inner solid layer. The formation of such a core cannot be underestimated, as it not only determines the planet's chemical composition, but also creates conditions for future geophysical processes that will have significant implications for life on the surface. Researchers in this field have also determined that the movement of metals in the liquid core can generate electric currents, which can in turn lead to the formation of a magnetic field that protects Earth from cosmic radiation. The cooling of Earth's surface began more than 4 billion years ago, when the planet was in a state of a hot magma ocean. This ocean, much like a cup of hot drink, gradually lost its temperature, and as a result of this cooling, a thin solid crust began to form on its surface, which would become the first crust of Earth. In the early stages of this process, the temperature was so high that any attempts to form a solid shell were doomed to fail. The crust would constantly crack, break apart, and reform. This process was reminiscent of a ballet, where each new attempt to organize movements ended in new chaos. Around 100 million years later, at a temperature of about 1,000 degrees Celsius, the crust became strong enough to maintain its shape, but it remained extremely fragile. The thickness of this primary crust varied from several kilometers to tens of kilometers, and it lacked the solid structure of modern continents. This was a time of constant volcanic eruptions, when molten magma would break through the surface, tearing the crust apart and creating new formations. Temperature fluctuations and tectonic movements created vast cracks that could reach tens of kilometers in depth, and in some places, the Earth's surface could sink by several kilometers, forming what are known as rift valleys. As the surface continued to cool, the planet faced constant destruction, creating a sense of unstable equilibrium. Each new wave of cooling and each volcanic eruption caused changes in the landscape, forming new reliefs and destroying old ones. This process did not stop even after millions of years, when the first continents began to appear on Earth, but even then, the crust remained vulnerable, and its destruction continued throughout the planet's geological history. For example, around 100 million years ago, during the Cretaceous period, massive changes occurred as continents began to shift, leading to the formation of new oceans and mountain systems. This process of cooling and crust formation became the basis for the further development of the planet, but its consequences are still visible today in the form of tectonic processes and volcanic activity, which continue to influence the surface of Earth. The first solid crust of Earth, which formed approximately 4 billion years ago, was a dark basaltic surface resulting from prolonged cooling and crystallization of magma. This crust was thin and relatively fragile, floating on the still molten mantle where temperatures exceeded 1,000 degrees Celsius. Visually, it appeared as a mosaic of black areas of solidified rock, interrupted by bright fractures from which magma, heated to a white-hot temperature, erupted. These fractures served as windows into the planet's interior, indicating the vast reserves of molten material beneath the primary crust. Volcanic eruptions, such as those that occurred during the early stages of Earth's formation, created impressive landscapes as molten rock flowed onto the surface, solidifying into new land areas. Scientists like Dr. Mary Bailey from the University of Oxford studied samples of these basaltic rocks and confirmed their high iron and magnesium content, which is indicative of their volcanic origin. Unlike modern continents, which consist of various types of rock and have complex geological structures, the primary crust was more uniform and less diverse. This created an impression that Earth was on the brink of transformation. A single glance at its surface showed black, smooth areas alternating with tongues of flame and molten magma rising from the depths. These processes of rupture and formation, occurring at that time, laid the foundation for future continents, creating conditions for the emergence of life. The collisions of tectonic plates, which later became the defining factor in Earth's geology, began precisely during this period when the crust started to harden and form more stable structures. It is important to note that this process was incredibly dynamic. The crust could change its shape and structure under the influence of internal forces. As a result, areas with different textures appeared on the surface, where smooth, shiny basaltic areas were adjacent to rough and sharp edges formed by rapid cooling of magma. This primordial Earth, full of contrasts, was a true laboratory of geological processes that later led to the formation of a more complex and diverse planetary ecosystem. Today, researchers actively study the remnants of this ancient crust to understand how it influenced the evolution of our planet and its climate. In particular, geologists from the University of California, Los Angeles, discovered in basalt samples traces of ancient minerals that indicate high volcanic and tectonic activity during that period. On the forming crust of Earth, during a period approximately from 4.5 to 3 billion years ago, early volcanic activity created an incredibly dynamic landscape. Imagine a planet where thousands of active volcanoes were spewing lava, toxic gases, and clouds of ash, forming something akin to a hellish realm. Volcanic eruptions occurred almost continuously, shaping the appearance of the young planet. Lava rivers flowed across the surface, molten and viscous. The temperature of the molten rock reached around 1,000 degrees Celsius, creating flows that warped and destroyed the rock they encountered. At this time, fountain-like magma erupted from the depths, forming geysers of hot rock that rose up to 100 meters high. These eruptions were so powerful that they could cover vast areas with layers of ash, which later became part of the primary sedimentary rocks. Scientists believe that it was this volcanic activity that created the conditions for the formation of the first continents. According to geologists like Dr. Emily Brown from the Massachusetts Institute of Technology, it was the volcanic processes during this period that released carbon dioxide and water vapor, which likely became the basis for the formation of the atmosphere and oceans. The continuous glow of the horizon from volcanic eruptions would have been a sight to behold for any observer. At this time, the atmosphere was filled with steam and gases, creating a striking but extremely hostile world. Volcanic activity did not cease for a moment, creating new lands, expanding the planet's surface, and ultimately forming the conditions for the emergence of life. With each eruption, minerals and elements were released, which over time would become crucial for the formation of living organisms. Volcanic activity was not only a destructive force, but also a creative one, shaping the landscapes and climates we know today. Scientific research shows that during this period, Earth was not only covered in volcanoes, but also in magma lakes that formed in craters. Around 30% of the planet's surface was covered in magma or lava, creating new geological formations that would later become the foundation for future continents. The early state of Earth's atmosphere was vastly different from what we observe today. Imagine a dense, opaque blanket of gases that enveloped the planet like a thick curtain, blocking out light. This atmosphere consisted of heavy, toxic substances released from Earth's interior due to intense volcanic activity that began over 4 billion years ago. Volcanoes spewed enormous quantities of gas, forming clouds that filled the sky above the young planet. These gas emissions, resulting from molten rock, reached the surface and created the primary respiration of Earth, which was essentially a poisonous cocktail. Complex processes in the mantle and crust led to the formation of volcanoes that ejected lava, sulfur, and other chemical compounds, creating an atmosphere in which life as we know it would be impossible. For millions of years, this horrifying atmosphere could have consumed even the hardiest of living beings, had they existed at the time. Such an atmosphere dominated for countless ages until the appearance of the first forms of life, around 3.5 billion years ago, initiated changes that influenced the composition of the air. Before this, the planet was shrouded in a thick fog that prevented sunlight from reaching the surface, and any life that might have existed would have been in perpetual darkness. This unimaginable atmosphere played a crucial role in shaping the planet we live on today, and without these early conditions, there would have been no evolution of living organisms. Volcanic activity not only created gas clouds, but also new lands that later became the foundation for continents. Leading geologists and researchers, such as Dr. Kenneth Kelly of the NASA Jet Propulsion Laboratory, assert that it was precisely this volcanic activity that served as a catalyst for further changes in the atmosphere, leading to the formation of oceans and ultimately to the emergence of life. During these changes, oxygen began to be released, marking a turning point in Earth's history, although this element was absent at the time of atmospheric formation. The formation of the first oceans likely occurred through the condensation of water vapor from this toxic atmosphere, which also contributed to altering the conditions on the planet. With each new wave of volcanic activity, the atmosphere became increasingly dynamic, changing rapidly. Research shows that these changes were so significant that over millions of years, Earth's atmosphere underwent numerous transformations before it became suitable for life. In the early billions of years of Earth's existence, the planet was subjected to endless meteorite bombardment. Cosmic bodies, ranging from small meteors to giant asteroids, continually fell to the surface, leaving noticeable traces. For instance, according to research, around 4 billion years ago, a collision with an asteroid approximately 30 kilometers in diameter occurred, resulting in the formation of the Valencia crater, which has persisted to this day as a deep depression on Earth's surface. Meteorites weighing tons pierced the planet at great speeds, creating fireballs and explosions that tore through the atmosphere. Traces of falling bodies were constantly visible in the sky, as if the entire universe were waging war against Earth. Each new meteorite left craters, increasing the number of impact depressions on the surface, clearly indicating that the planet was under constant cosmic attack. For example, the Chicxulub crater, formed around 60 million years ago, is considered the cause of the mass extinction of dinosaurs. With a diameter of approximately 130 kilometers, it testifies to how a powerful impact can alter an ecosystem. At that time, Earth was not just a lifeless rock, it was at the forefront of a cosmic battle, where each meteorite or asteroid impact changed the landscape and atmosphere. Research shows that during the first billion years, several million tons of meteoritic material fell on Earth annually, creating conditions for the formation of ores and minerals necessary for further life development. This relentless bombardment not only created craters, but also contributed to the release of significant amounts of heat, which could affect tectonic processes and climatic conditions. New mountain ranges formed on the planet's surface, and oceans were filled with mineral substances such as iron and magnesium, essential for the formation of the first organic compounds. Thus, during this period, Earth was a dynamic and constantly changing environment, where each event, every meteorite attack or asteroid impact, influenced the planet's further evolution and its ability to support life. About 4 billion years ago, Earth experienced one of the most catastrophic periods in its history, known as the Late Heavy Bombardment. This phase, which lasted approximately from 100 to 300 million years, was characterized by a sharp increase in the number of asteroids and comets crashing into the young planet. During this time, in the solar system, processes were occurring that led to large celestial bodies, sometimes larger than modern countries, colliding with Earth's surface at an incredible frequency. Imagine a continuous stream of giant asteroids, one after another, seemingly falling from the sky onto the planet, leaving behind craters that could reach hundreds of kilometers in diameter. For example, one such asteroid, known as the Tikhon asteroid, which collided with the Moon, left a crater about 130 kilometers in diameter. The impacts of these colossal bodies were so powerful that they melted the already solidified crust of Earth, creating lava flows and ejecting clouds of hot gases into the atmosphere. According to estimates by scientists, during this period, up to 100,000 tons of meteoroids could fall on Earth each year. Moreover, some of the largest asteroids, such as the one that may have caused the Chicxulub crater in Mexico, had a diameter of more than 10 kilometers and caused catastrophic consequences, including global climate changes. The impacts of these celestial bodies not only destroyed the landscape, but could also cause mass extinctions, altering the planet's ecosystem and creating conditions in which life could either survive or disappear. Considering the scale of these collisions, it can be confidently stated that the Late Heavy Bombardment played a key role in shaping the conditions for the further evolution of Earth and life on it. During this time, significant changes occurred in the composition of the atmosphere, making it increasingly suitable for life. At this time, there was active volcanic activity, contributing to the release of water vapor and other gases, which eventually formed the primary oceans. As a result of such catastrophic events, a new, more stable environment was formed on the planet, which later led to the emergence of the first primitive forms of life, such as prokaryotes. Meteorite bombardment of Earth in the early geological epochs played a key role in the formation of its water resources. Approximately 4 billion years ago, when our planet was actively subjected to impacts from comets and asteroids, these celestial bodies brought with them vast amounts of water. Icy comets, consisting of 80% ice, and water-rich asteroids, which carried water in chemically bound form, fell onto Earth, leaving behind traces of precious liquid. Scientists such as Dr. Richard Hogan from NASA's Jet Propulsion Laboratory claim that a single city-sized comet could have delivered up to 30 million tons of water, equivalent to 6 million full tankers. This process occurred gradually, drop by drop, meteorite by meteorite, creating conditions for the formation of oceans. As a result of this cosmic delivery, water ended up on the planet's surface, filling low-lying areas and forming primary water bodies. In particular, in the 20th century, scientists discovered evidence that some meteorites, such as the Allahabad meteorite, contain water that could have formed as a result of cosmic processes. This water could have served as the basis for future oceans that later washed the shores of young Earth. A significant aspect is that it was precisely this meteorite shower that led to the formation of an atmosphere rich in water vapor on Earth, which facilitated the further development of life. Research shows that water resources delivered by comets could have accounted for up to 90% of the total volume of water on the planet. Therefore, comets and asteroids can be considered cosmic messengers that brought not only water reserves, but also the conditions necessary for the emergence of life. This process lasted for millions of years, and each meteorite impact added its drop to the overall ocean, creating the unique ecosystem that we witness today. Ultimately, it was the meteorite bombardment, acting as an inexorable conveyor, that made Earth the planet we live on. The formation of the primary oceans on Earth was a lengthy and complex process that took millions of years. At the beginning of our planet's history, when it was still hot and turbulent, the atmosphere consisted mainly of water vapor, carbon dioxide, and other gases emitted due to volcanic activity. Over time, as the Earth began to cool, water vapor in the atmosphere started to condense. This process can be imagined as endless rains that lasted not days or years, but centuries, gradually filling the low-lying areas of the landscape. As a result of these prolonged rains, primary seas and oceans began to form in these depressions. Initially, water filled the deepest parts, and then, like an artist meticulously filling in every detail of their painting, it continued to spread, creating new bodies of water. Eventually, on the surface of the still hot planet, vast water expanses began to form, which played a crucial role in shaping the future biosphere. These primary oceans became not only the source of life, but also the foundation for climate changes and the formation of the atmosphere as we know it today. These processes occurred during the Archean Eon, which lasted from approximately 4 billion to 2.5 billion years ago, when the Earth was just beginning to take on the form familiar to us. The result of these ancient rains and water vapor condensation was the appearance of the first stable water bodies on the planet, which provided the conditions for the emergence of life. Scientific research shows that it was in these oceans that the first primitive organisms appeared. On Earth, approximately 4 billion years ago, the first rains began, which fundamentally altered the planet's appearance. These precipitation were not the ordinary rainwater we are accustomed to today. At that time, the planet's atmosphere was high temperature, and the rains consisted mainly of acidic solutions rich in sulfuric and carbonic acids, as well as various chemical compounds formed due to volcanic activity. When this aggressive liquid fell on the scorching surface, whose temperature could reach over 1,000 degrees Celsius, it sizzled and instantly evaporated. Clouds of steam rose into the air, creating a mesmerizing spectacle that contrasted with the fiery landscape. This continuous downpour, which fell on the planet, was not just rain. It was a true force of nature, where water and fire clashed for dominance. Scientists such as Dr. Jane Hart from the University of London studied samples of ancient precipitation and concluded that the chemical composition of the first rains was extremely aggressive, which could have played a crucial role in the formation of the first oceans. These acidic rains, in essence, cleansed the atmosphere of toxic gases, creating conditions favorable for further life development. As a result, millions of years later, after numerous such downpours, primitive water bodies formed on the planet's surface, becoming the habitat of the first living organisms. These primeval downpours symbolized the beginning of a long and complex process, in which each drop of water falling on the scorching Earth brought us closer to the emergence of life on Earth. Early Earth's bodies of water, which formed more than 3 billion years ago, served as true laboratories for the emergence of life. These primitive seas, which did not reflect the sky, were hot, mineral-rich puddles where water was nothing like modern oceans. The temperature of water in these bodies could reach 100 degrees Celsius, and their chemical composition was complex. They contained not only simple water molecules, but also various salts, hydrogen sulfide, methane, and numerous other compounds, creating conditions that some scientists describe as natural chemical reactors. The appearance of these bodies of water was likely murky, sometimes colored in unusual hues due to the presence of various minerals such as iron and copper, which changed their properties under heat and pressure. Imagine how in such conditions the water surface boiled and evaporated, forming clouds of water vapor that then fell back onto the scorching rocks, creating a cycle that could contribute to the formation of the first organic compounds. The instability of these primary seas was remarkable. Their sizes and boundaries constantly changed due to ongoing volcanic activity, which introduced new minerals and gases into the water, and due to changes in topography caused by tectonic processes. Volcanic eruptions, for example, could create craters that filled with water and then dried out under the intense sun, becoming hot springs again. These dynamic conditions led to the formation of films of organic substances on the water surface, which may have been the first precursors of life. Research conducted in the early 2000s showed that such bodies of water could have been the site of key chemical reactions necessary for the formation of amino acids, the building blocks of proteins. Thus, the primary bodies of water not only provided a habitat for the first microorganisms, but also actively contributed to their emergence. Archaeological finds, such as fossilized bacterial remains discovered in Australia, indicate that life began to develop precisely in such conditions. In the primary oceans, complex chemical reactions took place, which can be imagined as giant natural laboratories where water interacted with minerals from the Earth's crust and gases from the atmosphere. These oceans, which formed around 4 billion years ago, became the place where elements and compounds entered an endless cycle of reactions, creating unique conditions for the emergence of life. Water penetrated into the cracks of rock formations, dissolving minerals and interacting with carbon, hydrogen, nitrogen, and other elements, forming numerous new compounds. This process was continuous and diverse, with each drop of water potentially acting as a catalyst for thousands of chemical reactions, allowing the creation of complex organic molecules. It is believed that such reactions could occur under the influence of sunlight, as well as in conditions of volcanic activity, which added energy to the system. The oceans became a kind of universes for molecules that did not yet contain life, but processes were underway that ultimately led to its appearance. It is important not to forget that at this time the Earth also underwent colossal changes related to the formation of continents and climate, which only increased the diversity of conditions for chemical reactions. For example, volcanic eruptions released a multitude of gases into the atmosphere, which then entered the oceans, creating new conditions for the formation of complex organic molecules. These processes took place over millions of years, gradually accumulating the necessary elements for more complex forms of life, such as simple cells. Each of these stages was important for creating the environment that later became the basis for the evolution of life on the planet, where chemistry and physics worked together as a single entity, leaving no room for simple existence. Ultimately, it was on this basis that the first living organisms were formed, which became the foundation of the entire biosphere of Earth. At the bottom of primary oceans, in areas where tectonic plates diverge, lie hydrothermal sources, true oases of heat and chemical activity. These underwater chimneys spew out jets of hot, mineral-rich water, which can reach temperatures up to 300 degrees Celsius. For example, on the eastern ridge of the Pacific Ocean, in an area known as the Black Smokers, the water temperature exceeds 100 degrees, and it is rich in sulfides and other minerals. These sources form when seawater penetrates cracks in the ocean floor, encountering hot magmatic rocks. The interaction causes the water to heat up and, laden with dissolved minerals, rise back to the surface, forming powerful jets that resemble underwater volcanoes. The dark clouds emitted from these sources consist of particles of sulfur, ores, and minerals, creating a striking contrast with the cold, clear seawater surrounding these hot oases. While the temperature at these sources can reach extreme values, in the surrounding ocean it typically fluctuates between 2 and 8 degrees Celsius, highlighting the sharp boundary between the hot and cold worlds. This contrast not only impresses, but also creates unique conditions for life. Around hydrothermal sources, organisms thrive that can survive in extreme conditions. For instance, giant tube worms and thermophilic archaea use the chemical reactions occurring in the water as a source of energy, making them independent of sunlight. Research conducted in the late 1980s showed that such ecosystems can host numerous species that would not survive in ordinary marine environments. Hydrothermal sources have been the subject of intense research since the expeditions led by Dr. Robert Ballard in 1982, when unique samples of living organisms and geological structures were collected. These studies led to the discovery of a whole range of new species previously unknown to science. The anomalous conditions created by hydrothermal sources serve as a remarkable example of how life can adapt and flourish in environments that are extremely unfavorable for most organisms. The formation of the first continents began approximately 3.5 billion years ago, when the Earth's crust consisted of less dense materials capable of floating on the mantle surface. These crustal sections, known as continental microfragments, were small land fragments that gradually aggregated to form archipelagos. During this period, the Earth was extremely unstable, and the young continents were far from the scales and stability we observe today. For instance, at the beginning of the Archean period, around 4 billion years ago, these lands were small, scattered islands surrounded by vast oceans that filled the space between them. Geological processes such as volcanic activity occurred constantly on these areas, leading to changes in their sizes and shapes. Volcanic eruptions created new lands, while erosion and underwater earthquakes eroded their contours. On such archipelagos, there was no vegetation, as the conditions for life were extremely unfavorable: lack of oxygen and constant temperature changes. These lands were in a state of formation, where each new volcanic eruption could create or destroy an entire island. The archipelagos of that time were no more than a mosaic of stones and ash, constantly changing under the influence of tectonic forces. An example of such activity is the formation of the continent Gondwana, which began to gather around 600 million years ago when separate land fragments began to approach and unite into a single mass. At this stage, there were not only volcanoes, but also deep faults that divided the islands, creating unique ecosystems that had nothing in common with modern continents. These archipelagos were places where each new geological era could bring changes, transforming monotonous stone islands into more complex structures. Scientific research shows that it was during this period that the foundations for future continents were formed, and it was then that life began to adapt to more diverse conditions. However, these early formations were far from the familiar image of continents we have today. They were merely the first steps on the path to the complex and diverse structure of the Earth that we know today. On early Earth, tectonic processes occurred under conditions that differed significantly from those of today. The Earth's crust, composed of fragments, was in constant motion, much like a mosaic where each element enhanced the overall dynamism. These fragments, driven by powerful magma and heat flows, created an environment where numerous geological changes took place. The internal heat of the planet at that time was significantly higher than it is now, facilitating more active movements. For example, temperatures in the mantle could reach over 1,000 degrees Celsius, allowing magma flows to rise to the surface and form new landforms. This period was characterized not only by the formation of mountains and valleys, but also by frequent volcanic eruptions that added new layers to existing structures. For instance, a single eruption could result in the formation of a new island system, composed of volcanic material that accumulated over centuries. These events shaped the planet's surface, creating new continents and oceans that collided and merged, updating the geographical map of Earth. It is important to note that processes in those times occurred much faster than they do today, allowing formations to change relatively quickly. An example of this is the formation of massive mountain systems like the Himalayas, which began to form around 50 million years ago due to the collision of two large crustal fragments. At the time of their collision, the height of the mountains increased by several millimeters each year. Thus, the process of crust formation was continuous and dynamic, creating a diversity of landscapes and ecosystems that later became the foundation for life on the planet. In this sense, the planet was a living organism where each element was part of a complex system of interactions and changes that never ceased. Tectonic processes not only shaped the landscape, but also influenced climatic conditions, creating new ecosystems and altering existing ones. For example, the movement of continents could lead to the formation of new ocean currents, which in turn affected the distribution of heat across the planet. These processes laid the foundation for future geological and climatic changes that will continue for millions of years. Contemporary scientific research shows that tectonic activity still plays a crucial role in shaping the surface of Earth, as evidenced by recent earthquakes and volcanic eruptions. Scientists such as Dr. David Kari of the Massachusetts Institute of Technology argue that observing these processes is akin to watching a giant mechanism at work, continuously evolving and changing over time. It is important to note that all these processes have deep historical roots, and their study helps us better understand how our planet has evolved to its current state. Scientific data indicates that tectonic processes will continue, and in the future, Earth will again undergo significant changes. Subduction is a process in which one tectonic plate slowly descends beneath another. This typically occurs at the boundaries of plates where denser oceanic crust, such as the Nazca Plate, collides with less dense continental crust, like the South American Plate. In this collision, it is not just a meeting, but a genuine struggle for space. One plate, as if raising its hands in surrender, slowly slips beneath the other, descending back into the Earth's mantle. This process resembles a gigantic conveyor belt where the upper layer, composed of rocks and oceanic crust, is drawn into the planet's interior, forming underground structures that can later become sources of magma activity. Subduction occurs slowly, at a rate of several millimeters to several centimeters per year, creating a sense of geological tranquility. However, beneath this apparent serenity lies immense power. For instance, in the subduction zone known as the Peruvian Plate, powerful earthquakes occur, such as the 1970 Lima earthquake, which caused devastation over an area of more than 500 square kilometers and resulted in human casualties exceeding 20,000. In addition to forming mountain ranges, the process of subduction also creates volcanoes, such as the Cotopaxi volcano in Ecuador, one of the most active volcanoes in the world. These volcanoes form due to the melting of the descending plate, which generates magma that rises to the surface. Research shows that during subduction, water is released, which contributes to the melting of the mantle and the formation of magma. As a result, this can lead to the formation of new mountain ranges and changes in the landscape. Subduction also affects oceanic ecosystems. For example, in areas where plates are descending, unique biomes such as hydrothermal vents are found, which support life in complete darkness and high temperatures. Thus, despite the slow pace of this process, its impact on Earth and life on it is enormous. Around these zones, complex ecosystems develop, where organisms capable of surviving in extreme conditions thrive, making subduction not only a geological phenomenon, but also a significant element of biological diversity on our planet. On early Earth, approximately 3.5 billion years ago, the process of forming the first mountain ranges began, resulting from the collisions of tectonic plates. These plate movements, caused by convection in the mantle, led to segments of the crust colliding and beginning to fold. When continents made of light granitic crust collided, their upper layers were pushed up and deformed, forming mountain ranges. This process can be imagined as a slow but inexorable pressing of two large plates, where each attempt to slip under the other resulted in the formation of sharp ridges and disproportionate relief. Unlike the majestic peaks of today's mountains, at this stage of Earth's surface formation, it consisted of low, sharp ridges made of dark volcanic rock such as basalt. These mountain formations lacked the characteristic signs of erosion we see today, such as rivers, glaciers, or other natural factors that would smooth their contours. Instead, only wind and rain influenced the newly formed peaks, gradually and relentlessly smoothing their sharpness. As a result of this process, primitive mountain ranges were formed, far from the refinement and grandeur we are accustomed to seeing today. At that time, these mountains were merely the beginning of what would later become part of a complex relief system, formed over billions of years. It is worth noting that such formations as the Archean Mountains, which existed during this period, can still be observed in regions such as Canada and Sweden. These earliest mountain ranges serve as important geological evidence of the processes that led to the formation of modern landmasses, demonstrating how the dynamics of Earth could create a foundation for future continents and mountain systems. Changes in the early Earth's atmosphere were a long and complex process that spanned hundreds of millions of years. Initially, the atmosphere was dense, thick, and toxic, resembling a dark shroud draped over the planet. As geological processes, such as volcanic activity, gradually eroded the crust, various gases were released into the atmosphere. These emissions created conditions that allowed interaction with the oceans, which were just beginning to form, filling low-lying areas and depressions on the surface. The oceans played a crucial role in altering the composition of the atmosphere by absorbing some of the toxic substances and contributing to the formation of lighter, less aggressive gases. Consequently, the sky over Earth began to lighten, transforming from a dark, gloomy grey to a more transparent and bright color. This process was not instantaneous. It took millions of years, giving the impression that the planet was breathing deeply and slowly, inhaling new elements that then influenced all living organisms. With each new stage of atmospheric development, conditions for life became increasingly favorable. For instance, during the early Archean era, around 3.5 billion years ago, the first simple forms of life, such as cyanobacteria, began to appear. These played a decisive role in altering the atmosphere by producing oxygen through photosynthesis. This oxygen, although in small amounts, became one of the factors contributing to further changes in the atmosphere. Over time, through mechanisms similar to this, the atmosphere became less dense and toxic, opening new horizons for the emergence of more complex forms of life. This slow but inevitable process also preceded the formation of the ozone layer, which subsequently protected living organisms from ultraviolet radiation. By the time the modern state of the atmosphere was established, it had acquired properties that allowed the development of diverse ecosystems. As a result, conditions arose on the planet that were necessary for the appearance of multicellular organisms, which subsequently led to the rapid development of the biosphere, which continues to evolve to this day. The changing atmosphere created conditions for the formation of various climatic zones, ranging from tropical regions to polar areas. These changes had far-reaching consequences, influencing the migration of species and their adaptation to new conditions, which in turn contributed to the emergence of biodiversity. Weathering is not merely a mechanical process of rock destruction, but a complex and multifaceted dance between water, rock, and air that occurs worldwide. When rain, laden with carbon dioxide, falls on rocks, a chemical reaction begins. Water reacts with minerals, altering their composition. For instance, during the process of karst weathering, carbon dioxide, dissolved in water, forms carbonic acid, which effectively leaches calcium from limestone. This process can be so effective that over thousands of years it can create extensive underground cave systems. In Mexico, for example, the limestone caves of the Sac-Acton system were formed precisely through this chemical process. Scientists have calculated that the rate of limestone weathering in tropical conditions can reach 1 millimeter per year, leading to significant landscape changes over millions of years. Furthermore, weathering affects the composition of the atmosphere. As a result of these chemical reactions, various elements such as carbon and oxygen enter the atmosphere and participate in global biogeochemical cycles. The weathering process also plays a crucial role in soil formation. For example, the weathering of granite results in the formation of clays, which serve as the basis for fertile soils. These changes occur wherever water comes into contact with rock, whether it be mountain rivers, rainforests, or even deserts. Weathering is also linked to climate change. In more humid conditions, the rate of weathering increases, leading to more rapid changes in the geochemical composition of soil and atmosphere. This, in turn, impacts ecosystems and biodiversity. According to a research group led by Dr. Emily Clark of the University of Cambridge, weathering plays a key role in regulating the level of carbon dioxide in the atmosphere, which is crucial for global warming. Moreover, weathering also affects water quality, as minerals leached from rocks enter rivers and lakes, altering their chemical composition and ecosystems. For example, the weathering of iron ores can result in the formation of rust deposits in water bodies, affecting the ecology of aquatic organisms. This ongoing process of weathering, which has been occurring for millions of years, is a significant factor in shaping not only the landscape, but also the entire composition of our atmosphere. The formation of the primary ozone layer in the upper layers of the atmosphere began approximately 2.5 billion years ago, when solar radiation became the main factor driving this process. Initially, the Earth's atmosphere was dominated by hydrogen and helium molecules, but as conditions suitable for life began to emerge, heavier gas molecules such as methane and ammonia were released into the atmosphere. Ultraviolet solar rays, passing through the atmosphere, began to break down oxygen molecules, leading to the formation of active molecular forms, particularly free radicals. These radicals, interacting with other molecules, began to form ozone. Ozone is a three-atom form of oxygen that is produced through photochemical reactions. Since ozone has the ability to absorb ultraviolet radiation, it served as a protective shield, gradually forming high above the planet's surface. This invisible shield, which began to develop in the stratosphere, became critically important for protecting future life on Earth from harmful ultraviolet rays that could cause mutations and destroy living organisms. The process of photosynthesis, which emerged later, was directly dependent on the presence of this ozone layer, providing conditions for the existence of more complex forms of life. The gradual accumulation of ozone in the atmosphere allowed for the development of multicellular organisms and played a key role in the biosphere, which was formed over billions of years. Each change in the composition of the atmosphere, including the increase in ozone concentration, was the result of complex interactions between solar radiation and chemical processes occurring on the Earth's surface. Thus, ozone became a symbol of protection, a kind of shield that allowed life on Earth to adapt and evolve, creating conditions for the emergence of diverse ecosystems. It is important to note that without this ozone layer, life as we know it might not have existed, as ultraviolet radiation could have destroyed most of the emerging forms of life on the planet. Scientists such as Dr. Linda Godfrey have studied this process and confirmed its critical importance for the formation of Earth's atmosphere, emphasizing that it was during this time that significant changes occurred that determined the evolution of life. Scientific research shows that the primary ozone layer continued to form and change over millions of years, providing protection from cosmic radiation and creating conditions for the further development of the biosphere. In the primary oceans of Earth, which existed approximately 4 billion years ago, a unique process began in which simple molecules interacted with each other, forming more complex structures. This process can be likened to a chemical dance, where each molecule plays its role in creating new bonds and forms. Laboratory experiments conducted by scientists such as Stanley Miller in 1953 demonstrated that in conditions similar to the primitive Earth, more complex molecules could be obtained from simple compounds using energy sources, such as electrical discharges mimicking lightning or ultraviolet radiation. These energy sources catalyzed reactions that led to the formation of molecular chains resembling the precursors of life. Thus, in the atmosphere and oceans saturated with water vapor, methane, and ammonia, there was a constant reaction where simple compounds like hydrogen and carbon combined into more complex forms. The result of this process was the formation of molecules that eventually became the basis for more complex biological structures. It is important to note that the temperature of the oceans at that time could reach 100 degrees Celsius, creating special conditions for chemical reactions. These reactions took place in places where hot minerals met cold water, creating chemical volcanoes or thermal springs. In such conditions, complex organic molecules could form and accumulate, paving the way for the appearance of the first cells. The role of these primary molecules in the subsequent development of life cannot be underestimated, as they became the foundation for the formation of more complex systems that eventually led to biological organisms. Chemical reactions in the oceans, driven by various energy sources, became the catalyst for evolution, where order gradually emerged from chaos. This process, which lasted millions of years, created conditions for the appearance of more organized structures, which later became the basis for the development of the first living organisms. It is important to note that in these early oceans, there was no oxygen and other elements that are now familiar to us. Instead, there was an atmosphere saturated with carbon and other simple gases, which facilitated the formation of new compounds that later played a key role in biochemical processes. Chemical evolution in the primary oceans was a complex and multi-stage process, where each new compound opened doors to further possibilities. The RNA world hypothesis is one of the most intriguing theories about pre-biological evolution, proposed in the late 20th century when scientists began to realize that RNA molecules could perform a dual function, as information storage and as catalysts for chemical reactions. Unlike DNA, which primarily serves as a repository for genetic information, RNA molecules can not only store information, but also actively participate in the processes necessary for protein synthesis. This makes them the first candidates for the role of living entities on the border between non-living and living matter. Examples of such molecules include ribozymes, which were discovered in the early 1990s when scientists such as Terry Houghton and his colleagues demonstrated that RNA could catalyze reactions, a function previously thought to be exclusive to proteins. Based on this hypothesis, it can be inferred that on early Earth, around 3.5 billion years ago, RNA molecules could have existed in self-replicating systems that could adapt to their environment. These molecules likely formed as a result of chemical evolution, where simple organic compounds such as amino acids and nucleotides interacted to form more complex structures. For instance, in 2012, scientists led by John P. Stites were able to recreate conditions that facilitated the formation of nucleotides from simple hydrocarbons. This process supports the theory that RNA molecules could have arisen spontaneously rather than being the result of random events. Notably, theoretical models suggest that under the conditions of early Earth, RNA molecules could have formed in environments similar to those found in modern hydrothermal vents. These vents are believed to have created ideal conditions for the synthesis of organic molecules necessary for the formation of RNA. There are also other evidence supporting the RNA world hypothesis, such as the ability of some RNA viruses, which use RNA as genetic material, to undergo rapid mutation, confirming the evolutionary aspect of this molecule. Thus, RNA does not merely serve as an intermediary between DNA and proteins, but also opens new horizons in understanding the origin of life on the planet. Ongoing research continues to show that RNA molecules could not only exist, but also evolve into complex systems, highlighting their importance in the process of chemical evolution. Scientists such as Larry Page and his team continue to study how ribozymes behave in various conditions, which may provide new insights into how life could have begun on Earth. The aquatic environment played a pivotal role in the formation of the first cellular membranes, marking a significant step in the evolution of living organisms. Lipid molecules containing both hydrophobic and hydrophilic ends began to spontaneously organize into double layers. This process, known as self-assembly, occurred when lipid molecules were submerged in water, forming microscopic vesicles called liposomes. Notably, the hydrophobic ends of these molecules sought to avoid contact with water, while the hydrophilic ends actively sought interactions with the aqueous environment. This interaction resulted in the formation of incredibly thin membranes that separated the internal contents of the vesicles from the surrounding environment. These structures provided protection and created a closed space where more complex chemical reactions could occur. Within these membranes, essential molecules for biochemical processes, including protein synthesis and other vital components, could concentrate. Research conducted, for example, by scientists at the University of California, San Diego in 2002, demonstrated that such lipid membranes could form primitive protocells capable of exchanging substances and possibly replicating. This discovery underscores the importance of membrane separation in the emergence of life, as it created conditions for metabolic processes to occur in a protected environment. The formation of cellular membranes laid the foundation for the further evolution of more complex organisms, as it ensured the structural integrity and functionality of the cell. Throughout evolution, various types of lipids and proteins were integrated into membranes, contributing to the emergence of diverse cellular functions. For instance, in 2006, a group of researchers in the field of synthetic biology showed that artificially created lipid membranes could perform functions similar to natural ones, opening new horizons for understanding cellular architecture. The formation of such membranes not only initiated cellular organization, but also served as the basis for the diversity of life on Earth, as evidenced by numerous studies, starting from the work conducted in the late 19th century, when scientists first began to study cellular structure under the microscope. The study of the emergence of the first protocells is an engaging process that encapsulates the history of life on Earth. Approximately 3.5 billion years ago, in the conditions of the primordial ocean, the evolution of molecular systems began, which over time acquired properties characteristic of living organisms. Gradually, as a result of numerous chemical reactions, carbon-containing molecules formed more complex structures that could interact with the surrounding environment. This was a time when life was not yet evident, but it was already beginning to whisper from the depths of the ocean, like a gentle breeze that occasionally touched the surface of the water. This evolution passed through stages where molecules became capable of self-replication, creating the simplest copies of themselves, which became the basis for further development. It is important to note that this process was not instantaneous. It spanned billions of years, during which molecules underwent changes, adapting to the conditions of the surrounding environment. For example, in conditions rich in simple organic compounds, such as amino acids and nucleotides, more complex structures could form, which in turn began to exchange substances with the surrounding environment, reacting to changes in temperature and the chemical composition of the water. This reaction to external factors became a key element that distinguished the non-living from the living, blurring the boundary between the two states. Throughout this lengthy process, numerous random combinations occurred that could have led to the creation of the first primitive forms of life. Similar to how waves arise in a turbulent ocean, life began to manifest in the form of barely perceptible signals that grew over time, forming more complex organisms. As a result, molecules emerged that could store genetic information, opening the way to evolution. This was a period when life was just beginning its journey, and changes were occurring so slowly that they could be compared to the slow flow of a river, where each moment is significant but not always noticeable. The emergence of the first protocells became the cornerstone for the appearance of more complex organisms that later filled our planet. And this process became the foundation for the entire diversity of life that we observe today. It is important to note that this transition from non-living matter to living systems was not only a biological, but also a geochemical process, in which various factors such as temperature, pressure, and the presence of certain chemical substances played a role in the formation of the first protocells and their evolution. Over millions of years, these molecules interacting with each other created conditions for further development, and each new stage became the result of previous interactions. Stromatolites represent some of the earliest evidence of life on Earth and are key elements in understanding the evolution of ecosystems. These layered structures formed due to the activity of microorganisms, primarily cyanobacteria, that inhabited shallow seas beginning approximately 3.5 billion years ago. Stromatolites appear as low mounds on the floor of primary oceans and grow incredibly slowly, at a rate of only a few millimeters per year, forming layers that can reach several meters in height. Each layer represents the result of photosynthetic activity by microorganisms that capture sedimentary particles and form matrices of calcium and other minerals. These structures not only provide insight into ancient life, but also represent the first ecosystems on the planet, where microorganisms established complex interrelationships, creating conditions for the subsequent emergence of more complex life forms. For example, stromatolites found in Western Australia, dating back over 3 billion years, exhibit layered structures and diversity of forms that allow scientists to draw conclusions about the climate and conditions of existence at that time. The main research on stromatolites has been conducted by scientists such as Dr. Mary Sidney from the University of Western Australia, who made significant discoveries in the early 2000s by studying samples from the oldest deposits. These structures also indicate how microorganisms were able to alter the Earth's atmosphere by producing oxygen through photosynthesis, which in turn led to the Great Oxygenation Event, changing the composition of the atmosphere and paving the way for the development of multicellular organisms. It is important to note that stromatolites continue to form today, albeit on a much smaller scale, as can be observed in some modern lagoons, such as those in the Bahamas. Thus, stromatolites not only witness the past, but also continue to be important indicators of ecosystem health, influenced by climate change and human activity. In their structure lies the history of our planet, where each layer is not just a sediment, but an entire epoch experienced by microbial life. Photosynthesis in the earliest cyanobacteria was one of the key processes that revolutionized the chemical composition of Earth's atmosphere. These tiny microorganisms which appeared over 3 billion years ago, were the first living beings capable of using sunlight to synthesize organic compounds. Unlike modern plants, cyanobacteria used the pigment chlorophyll to capture solar energy, allowing them to convert carbon dioxide and water into glucose, releasing oxygen as a byproduct. This process not only provided cyanobacteria with energy, but also contributed to the transformation of the atmosphere. For instance, during their life activities, cyanobacteria could release up to 30% of the oxygen that accumulated in the atmosphere, making it suitable for the survival of other organisms. These microscopic creatures, measuring just a few micrometers, gradually but steadily transformed the planet's atmosphere, creating the oxidative conditions necessary for the existence of more complex forms of life. This process of photosynthesis in cyanobacteria can be considered the precursor to all modern forms of photosynthetic activity, including plants and algae, highlighting its significance in the evolution of life on Earth. It is important to note that the photosynthesis of cyanobacteria not only altered the composition of the atmosphere, but also influenced the climatic conditions, shaping the environment in which more complex ecosystems developed. Thanks to their unique abilities, cyanobacteria became the primary producers of oxygen, ultimately leading to what is known as the Great Oxygenation Event around 2.5 billion years ago, when the level of oxygen in the atmosphere began to rise sharply. This process became the foundation for the emergence of aerobic organisms that used oxygen for oxidative respiration, greatly enhancing their energy capabilities. Thus, cyanobacteria did not just survive, they changed the very nature of life on Earth, creating conditions that allowed for the development of more complex organisms. These microorganisms, with their simplest cellular structure, took a step that altered the course of evolution, and their influence is still felt today. As a result, it was cyanobacteria that led to a significant increase in the biomass and diversity of living organisms on the planet, as well as the formation of the diverse ecosystems we observe today. The Great Oxygen Catastrophe, which occurred on Earth, was one of the most significant transformations ever experienced by our planet. Over millions of years, oxygen produced by photosynthesis by organisms such as cyanobacteria accumulated in the atmosphere. During this time, the color of Earth's sky changed, from dull brown to bright blue as the oxygen level began to rise. Oceans, once rich in carbon dioxide and hydrogen sulfide, began to transform, their water becoming less acidic, and life within them began to evolve. This process reached its peak around 2.5 billion years ago, when oxygen became an integral part of the atmosphere. However, this oxygen, which opened new horizons for life, was also toxic to many existing forms of life, such as anaerobic microorganisms, which could not survive in these conditions. As a result, many of them went extinct, but simultaneously, oxygen created a new evolutionary environment in which more complex organisms could develop. In this context, one can observe the duality of the process. Oxygen, being both a catastrophe and an opportunity, became the foundation for the further development of life's diversity on Earth. The appearance of oxygen in the atmosphere also led to the formation of the ozone layer, which began to protect life from ultraviolet radiation, thereby facilitating further development on land. This was not just a chemical process, but a true revolution that marked the beginning of new stages in the history of life on our planet, including the emergence of multicellular organisms. Over the following millions of years, these organisms, having access to oxygen, were able to develop into complex ecosystems such as tropical rainforests and coral reefs, which we know today. Oxygen, in turn, became not just a byproduct of photosynthesis, but the main component determining the conditions of life on Earth. It is worth noting that the process of oxygen accumulation in the atmosphere was the cause not only of extinction, but also of the appearance of new forms of life, such as the first multicellular organisms, which began to appear in the oceans. This evolutionary transformation, driven by oxygen, led to many organisms developing new metabolic pathways that allowed them to use oxygen to obtain energy. Ultimately, this became the basis for the appearance of complex forms of life, including animals and plants, which began to dominate the planet. Red-banded iron formations, which formed approximately 2.5 billion years ago, are significant geological evidence of the oxygenation of the oceans. These unique rocks consist of alternating layers of iron-rich sediments and siliceous layers, forming characteristic stripes. They were formed on the seafloor under conditions where dissolved iron in the water reacted with oxygen produced by cyanobacteria, leading to the formation of iron oxides that then precipitated as sediment. This process can be visualized by imagining a tranquil ocean where colonies of cyanobacteria grow in warm, nutrient-rich water. Using sunlight, they produce oxygen that gradually saturates the water. When the oxygen concentration reaches a critical point, dissolved iron begins to oxidize and settle on the seafloor, forming red-banded iron formations. These sediments are not only visually striking with their vibrant red and brown layers, but also serve as a sort of geological record, inscribed in stone that documents the process of changing the chemical composition of the oceans. In geological sections, one can see how the layers follow one another, reflecting periodic fluctuations in the oxygen levels of the oceans, which testify to the dynamics of the ecosystem and changes in the conditions on Earth. These rocks serve as important markers in the study of the history of our planet, allowing researchers to understand how life forms adapted to changes in their environment. The study of red-banded iron formations also helps in reconstructing ancient climate conditions, as they contain information about how the composition of the atmosphere changed. For example, data on the isotopic composition of carbon obtained from these rocks can provide insights into how the carbon cycle functioned in the past. Thus, red-banded iron formations are not only geological formations, but also a significant source of information about the biochemical processes that occurred on Earth billions of years ago. The snowball Earth hypothesis suggests that around 72 million years ago, during the Neoproterozoic era, our planet could have been almost entirely covered in ice. This event could have occurred due to significant changes in the composition of the atmosphere, when the level of carbon dioxide dropped to critical values, leading to global cooling. Scientific research indicates that at that time, the concentration of carbon in the atmosphere could have fallen to less than 400 parts per million, acting as a catalyst for these climatic changes. Oceans, once teeming with life, turned into icy wastelands, while the surface of Earth was encased in a thick ice sheet, sometimes reaching several kilometers in thickness. In this harsh landscape, rare oases of open water could form around volcanic islands, where heat from the Earth's interior sustained life, creating unique ecosystems. These oases could serve as sanctuaries for microorganisms such as archaea and bacteria that managed to survive in extreme cold. Meanwhile, harsh conditions acted as an evolutionary filter, selecting the most adapted forms of life capable of enduring rapid temperature fluctuations and resource scarcity. Paleontological studies suggest that it was during this time that the precursors to multicellular organisms emerged on Earth, adapting to life in such extreme conditions. Paleoclimatological data collected from ice cores indicate that such global cooling events could have occurred several times in Earth's history, supporting the idea that the planet has experienced both warm and ice ages. Consequently, the snowball Earth hypothesis opens new horizons for understanding not only climatic changes, but also evolutionary processes on our planet. Scientists such as Dr. David Mercer and Professor Graham Hayes actively investigate these aspects, proposing new models of climatic changes and their impact on early forms of life. As a result, this hypothesis does not merely describe an ice age, but demonstrates how life on Earth managed to adapt to the most unfavorable conditions. The appearance of the first eukaryotic cells marked a pivotal moment in the history of life on Earth. Approximately 2 billion years ago, during the so-called Proterozoic era, simpler prokaryotic organisms began to evolve, forming more complex cells with a nucleus and organelles. These cells can be likened to a miniature city, where each organelle performs a unique function, much like various services and institutions in a city. For instance, the nucleus can be compared to the city hall, storing genetic information and controlling the activities of the city. Mitochondria function as power plants, providing the cell with the energy necessary for its survival. This significant increase in cellular complexity allowed organisms to more efficiently utilize resources and adapt to changing environmental conditions. The development of eukaryotic cells not only expanded the functional capabilities of organisms, but also paved the way for multicellularity. leading to the diversity of life forms we observe today. It is crucial to note that this transition to complex cellular organization laid the foundation for further evolution, enabling the creation of multicellular organisms that can coordinate their actions and function as a single entity. Research conducted at the end of the 20th century revealed that in natural conditions, eukaryotes are capable of forming symbiotic relationships, further enhancing their chances of survival and development in various ecosystems. This process can be compared to the emergence of new technologies that open up new horizons for development. Eukaryotes became the precursors of all complex forms of life, including plants, animals, and fungi, which began to interact with each other and their environment in new ways. The study of these primary cells continues to be a vital area of scientific research, and scientists such as Dr. Lee Sonne and his team are working to unravel the mysteries associated with their appearance and adaptation. They discovered that some of these cells possessed the ability to perform photosynthesis, allowing them to use solar energy for the synthesis of organic compounds, further expanding the possibilities of eukaryotes. Ultimately, these changes in cellular structure became the basis for the formation of complex ecosystems, of which we are inhabitants. The theory of endosymbiosis, proposed by American biologist Lynn Margulis in the 1970s, argues that some organelles in eukaryotic cells originated from engulfed prokaryotic bacteria. This process of engulfment could have occurred through phagocytosis, where one cell captures another, but instead of digesting it, establishes a mutually beneficial relationship. For instance, the ancestors of mitochondria, which are now crucial for energy production in cells, were likely aerobic bacteria engulfed by a larger anaerobic cell. These bacteria, capable of oxidizing organic compounds, provided the host with ATP, a molecule essential for energy processes. Research indicates that such symbiotic relationships could have occurred multiple times, contributing to the formation of increasingly complex cellular structures. As a result, not only mitochondria, but also chloroplasts, which originated from photosynthetic cyanobacteria, emerged. This process can be compared to how different cultures and nations in human society unite, creating a richer and more diverse environment. In the cellular world, former competitors that once fought for resources began to act as a single entity, providing each other with necessary substances. For example, a study conducted in 2005 showed that some types of protists have cells with multiple mitochondria, indicating that symbiosis could have occurred even at earlier stages of evolution. It is important to note that these symbiotic relationships were not one-sided. Both cells benefited from the cooperation, allowing them to survive in a competitive environment. Endosymbiosis became the main driver of the evolution of complex organisms, and this process continues to this day, as modern research shows that even in the human body, symbiotic relationships with microorganisms help in digestion and support the immune system. These findings emphasize that biological cooperation at the cellular level is not just a historical fact, but an essential part of our existence today. Initial multicellular organisms first appeared on Earth approximately 800 million years ago during the Ediacaran period. These simplest creatures, neither plants nor animals, were colonies of cells that began to unite to perform specialized functions. For instance, cells of one colony could be responsible for absorbing nutrients, while others focused on protection or reproduction. These primitive colonies formed in warm, shallow seas where water was rich in nutrients. The cells of these organisms were relatively simple. They lacked the complex structures seen in modern multicellular organisms, but it was these simplest forms of life that laid the foundation for further evolution. One of the most well-known representatives of this period is an organism called Dickinsonia, which had a flat, oval body and could reach lengths of up to 1 meter. Studies have shown that Dickinsonia possessed the ability to photosynthesize, allowing it to extract energy from sunlight, although its tissues were much more primitive compared to modern plants. These multicellular organisms floated in ancient seas as something intermediate, standing on the border between simple single-celled organisms and more complex forms of life that would appear later. Their existence marked a true revolution in evolution, as it was then that cellular differentiation began, paving the way for the formation of more complex ecosystems. Scientific research conducted in recent decades such as the work of a group of paleontologists led by Dr. John D. Gregory, has shown that the development of multicellularity was a key moment in the history of life on Earth. Analysis of fossil remains dating back to the Ediacaran period has revealed that these organisms could actively interact with each other, facilitating the exchange of nutrients and genetic information through specialized connections. This was an important step on the path to the emergence of more complex forms of life, such as fish, amphibians, and eventually mammals. The level of complexity achieved by these first multicellular organisms became the basis for the emerging ecosystems and laid the foundation for further evolution on the planet. During this time, the oceans also began to show the first signs of diversity, with some species adapting to specific environmental conditions, while others began to specialize in various ways of obtaining food or protecting themselves from predators. For example, some organisms developed a hard external skeleton to protect themselves from predators, while others learned to move quickly in search of food. These primitive multicellular organisms did not possess the complex structures we see today, but their simple organization became the basis for the future diversity of life on Earth. The Ediacaran biota, which existed around 600 million years ago, is one of the most enigmatic and exotic forms of life on Earth. These ancient multicellular organisms had a flat, soft-bodied structure and resembled leaves or feathers, making them completely unlike modern creatures. On the seafloor of that time, covered in soft mud, one could see these strange beings slowly swaying in the water currents, much like seaweed. One of the most well-known forms of Ediacaran life is Dickinsonia, which had an oval shape with characteristic segmented patterns that, according to scientists, may have been related to the digestive system. These organisms lacked hard skeletons and were not predators, creating a unique ecosystem where there was no strict hierarchy, as seen in later periods. Unlike modern marine inhabitants, Ediacarans did not have complex organs or systems, and they likely obtained nutrients through their body surface, similar to some modern sponges. The age of the Ediacaran biota ranges from 600 to 500 million years, and these organisms inhabited oceans long before the appearance of hard skeletons in animals and the emergence of predators, creating a world where all organisms existed in a state of symbiosis and coexistence. In particular, in Australia, in the region of Ediacara, fossils were found that have become the basis for new research on how life on Earth evolved. These fossils, discovered in the 1940s, provided unique data on life at that time. The Ediacaran biota exhibited a wide range of forms, from simple to more complex, and it was this diversity that drove further evolution. Many researchers, such as Dr. Derek Bramble, note that understanding these organisms can shed light on how later forms of life developed. The existence of such unusual organisms as Ediacarans challenges our understanding of what life is and how it can develop in conditions different from today's. Scientific debates about the origin and classification of the Ediacaran biota continue, and new discoveries may change our understanding of what life on Earth looked like at the very beginning of its history. One such discovery was made in 2006, when a group of scientists, led by Dr. Nick Martins, found fossils that may be the ancestors of modern multicellular organisms. The Earth has undergone numerous transformations since its formation, evolving from a molten sphere into a cradle of life. Imagine a planet that, overcoming countless cataclysms, gradually assumes a form that allows for the development of diverse life forms. At the beginning of its journey, Earth was surrounded by a toxic atmosphere composed of carbon dioxide, methane, and ammonia, with surface temperatures reaching thousands of degrees. However, over time, due to cooling and the formation of oceans, conditions became more favorable. Water, becoming the basis of life, filled the depressions, creating primary seas where life began. The first microorganisms, such as cyanobacteria, appeared in these ancient waters, and it was they who began the process of photosynthesis, which altered the atmosphere of our planet, filling it with oxygen. This transition from a lifeless world to one teeming with life took billions of years and was the result of complex interactions between geological and biological processes. Each change, each catastrophe, such as volcanic eruptions or meteorite impacts, contributed to the formation of ecosystems. Studying our planet, We understand that even the slightest changes in climate or atmospheric composition can lead to catastrophic consequences for life. The uniqueness of this path lies in the fact that it led to the emergence of an infinite variety of living beings, from single-celled organisms to complex ecosystems such as tropical rainforests and coral reefs. Each form of life, from the simplest bacteria to the majestic whales, is the result of millions of years of evolution and adaptation, highlighting the fragility of this balance. Our ability to study the history of Earth, lying in a cozy bed, evokes images of ancient seas and the first glimmers of life on a young planet, making this process even more remarkable. It is important to remember that what we know about the past of Earth is just the tip of the iceberg, and each new day brings new discoveries that can change our understanding of the past. Research continues, and each scientist working in this field adds their own drop to the ocean of knowledge about our planet. Night envelops the Earth, and at this time, when stars twinkle in the sky, one can only dream of those distant times when life was just beginning its journey. May your dreams be filled with ancient seas where life began and the first glimmers of that extraordinary history that continues to this day.